Welcome to Classes with Atish. In today's lesson, we will talk about Newtonian mechanics. We will go over the three laws of motion. This is also called classical mechanics. So let me write that down. So we already talked about kinematics in previous lessons. Kinematics is the study of the effect that a force has on a body. So we are more concerned with the state of the body, as in, is the body at rest? Is the body moving? How fast is it moving? Is its speed, velocity changing? Things like that. But as soon as we ask the question, why is the body in the state that it is in? That's when dynamics comes into the picture. Okay. So kinematics is study of state of the body. State of the body. Okay. And dynamics is the study of cause and effect. So why would the state of a body change? Whenever there is a change in state of a body, by state of a body I mean whether its velocity changed or maybe it was at rest and it started moving, things like that. The change is caused. Why it happened? The change is caused because of an external force. Okay. So when an external force acts on a body, that's when the change in state of a body happens. Okay. Now forces could be different types. Broadly we say there are four types of forces. One is the gravitational force, second is the electromagnetic force, third is what we call weak nuclear forces, and fourth is strong nuclear forces. But we will classify types of forces in, again, four different types. But let's talk about non-contact force. Okay, contact force, weak forces, and strong nuclear force. Okay. Now non-contact forces, examples would be, like I mentioned, gravitational force. Okay. We'll talk more about that. In fact, in this particular chapter, we'll talk a little bit about gravitational force. Contact force, examples will be like tension in a string, maybe the spring force. Okay. The third one could be like the normal reaction, and the fourth one is friction force. These are also called electromagnetic forces. Like, why is it called electromagnetic forces? Because it is thought that all these type of forces happens when atoms of a particular body interact with atoms of a different body or the same body. In case of tension force and spring force, it's atoms of the same body. In normal reaction and friction force, it is atoms of different bodies. When they interact with each other, they exert electromagnetic force on each other. So, okay. Weak force, we can say van der Waals force. We will study more about that in chemistry. These are forces that are exerted between molecules. And then also radioactive decay, that will qualify as weak force. Okay. Strong nuclear force is what holds the nucleus of an atom together. Okay, let's write that down. Holds nucleus of atom together. Like you can imagine, there are protons which are all positive charges. How are they held together? Positive charges should be repelling each other, right? That is overcome by the strong nuclear forces. Okay, so these are the four types of forces, but for the purpose of Newtonian mechanics, we will talk a little bit about gravitation, and we will also cover mostly about tension force, spring force, normal reaction, and friction force. Okay. Last thing before we move on, force is a vector quantity, so which means it has both magnitude and a direction. Alright. The other thing is SI unit of force is Newton, also kg meter per second square. Okay. Alright, with that, let's move on to describing some of these forces in a little bit more detail. Okay, the first force we'll talk about is gravitational force. Okay. Now, gravitational force between two masses m1 and m2 is minus g m1 m2 by r square, where r is the distance between those two masses. Okay, so if this is one body of mass, this is another, this one is m1, this is m2, then each exert a force on each other. So m2 attracts m1 towards itself with this force, and m1 attracts m2 towards itself with the same force. Okay, these forces are always directed towards the center of the body. In case of when you are on earth, okay, so let's say one of the bodies is earth and the other body is a smaller body that is residing on earth, then the force is mass times g, where g is a constant, 9.8 meter per second square. G is a constant near the surface of the earth. Okay, so we'll discuss about this one in more detail in later classes. Right now what we'll focus on is the gravitational force near, so let's say near the earth's surface, the force that is exerted on a mass m by the earth is mg, where m is the mass of the body and g is a gravitational constant. Okay, and the point here to remember is the force is directed towards the center of the earth. Okay, sometimes we do approximate this constant g as 10 meter per second square for ease of calculations. Okay, the next force that we'll talk about is normal reaction. Okay, the word normal means it's perpendicular. Okay, so always remember this normal reaction acts perpendicular to the point of contact. This normal reaction is a contact force. Now let's talk about this in a little bit more detail. Let's say there is a mass m, okay, it is resting on a surface. This mass m exerts a force on the surface, and that force is mg because there is a gravitational pull. Okay, the surface also exerts an equal and opposite force to the mass m. Why? Because if the only force that was acting on the mass m was mg, then the mass would have started falling. But what keeps it on the surface? What keeps it on the surface is because the surface also exerts a normal reaction force on the mass, and because this normal reaction force cancels out the weight of the body, which is mg, gravitational pull, it balances out. Okay, because the surface exerts a normal force n on the mass m, the mass m also exerts a normal force n on the surface. Okay, and also remember this normal force is perpendicular to this surface. Okay, let's take another example. Let's say there is a sphere, okay, and the mass m is now on this sphere. Okay, now what is the normal force that the sphere exerts on the mass m? It is n in this direction, which is 90 degrees. So this force, if we extend it to the center of the sphere, this force, the direction is like this. Similarly, the mass m also exerts a force n on the sphere, normal reaction on the sphere. Okay, so this is to illustrate that this normal reaction is always perpendicular to the point of contact. Similarly, if we take an inclined plane, okay, and let's say there is a mass that's sitting on this inclined plane. This plane, it exerts a normal reaction on the mass which is perpendicular to the point of contact, and the mass also exerts a normal reaction on the plane which is again perpendicular to this. Now these two ends don't cancel out because these forces are acting on different bodies. This is acting on the wedge, this end is acting on the mass. Okay, so remember that. Okay, next example we'll take is tension force. Such kind of tension force acts on strings, rods, chains, okay, mostly massless string, massless rods and chains. Okay, let's take an example. Let's say there is a string attached to the surface and there is a mass at the end of the string. Okay, now obviously this mass is being pulled by gravity, so there is a mg force acting on the mass, but then the mass is not falling down, right? So something must be also acting on the mass in the upward direction to keep it where it is. That is what this tension force is. So there is some tension in the string which balances out the weight of the body. That's how it is held in position there. Okay. One thing important to remember here is the direction of this tension force is always pointing away from the point. Okay, so it's always away from the point. Let's take another example. Let's say there is a body M, there a string is attached to the body and it is being pulled by a force F in this direction. Okay, so the tension force on the string T will be away from the body, away from the point. Okay, so make sure that the tension you don't direct it towards the body, it should always be away from the point. Okay, another example. Let's say there is a mass m2, there is another mass m1, they are attached with a string, and this m1 is being tugged by a force F. Okay, let's say there is a string here as well. Okay, this string will have some tension T1 which points away from the body. This string, there will be another tension T2 which points away from M1, same string T2 which points away from M2. Okay, if the string is continuous, okay, then tension remains same. Just remember that the tension that is acting on this body is always away from it. The direction is always away. Okay. Now This string and this string are different strings. Tension will be different if strings are different. Okay? Let's take another example. Let's say there is a body M. It is held by a string like this, and then this is also held by a string like this, and there is weight of the body acting this way. Okay? If this tension is T1, this tension is T2, always remember the tensions will be acting away from the body. Okay? If you look this way, this one will be T1. If you look this way, this one will be T2. So the T2 acting on the surface, T1 acting on the surface. These will be equal. Because the string is continuous, these two tensions are same. These two tensions are same. However, this tension and this tension is different. Also, do remember that the string is a massless string. Okay, that's an assumption. Now is a good time to introduce a concept called free body diagram. In short, FBD. Okay. Now, before I go into the details, few things you must always remember. Number one is the mass for which this free body diagram is being drawn is assumed to be a point mass. Okay. Number two, only show the forces that are acting on the mass. This is very, very important. Do not show the forces that the mass exerts on other bodies, but only show the forces that are acting on the mass. Okay. And number three, all forces must have a reference frame. As in, all these forces must be by the same observer. Okay. Because for different observers, the number of forces or even the magnitude of these forces could be different. Okay, so that is where that inertial and non-inertial frame of references concept will also come in. For these purposes, it is assumed that it's an inertial frame of reference and an observer is on the ground. Okay. Now with this, let's do a simple free body diagram. Let's say there is a mass M resting on a surface. Okay. Now let's draw the free body diagram of this mass. So what's the first force that is acting on M? Is the gravitational pull, mg, in the downward direction. There is another force that is acting on this M, which is the reaction by the surface at the point of contact. So that's the normal reaction. Okay. So the free body diagram for this, for the mass, is this. Let's take another example. Let's say the mass is now on this wedge. Okay. Now if we draw the free body diagram of this mass M, what will it be? So there would be gravitational pull in the downward direction. There would be a normal reaction which is perpendicular to the point of contact, which means this surface. Okay. Are there any other forces that are acting on this mass? No, that will be all. Let's take another example. Let's say there is a massless pulley attached to a string, and then there are two strings in here. There is a mass M1 here, and then there is a mass M2 here. Okay. If I say draw the free body diagram of the pulley of the mass m1 and m2, what would that be? Let's do for the mass m1 first. Okay. So m1, gravity is pulling it in the downward direction, m1g. There is a tension in the string that is pulling the mass in the upward direction, that is T. Okay. If we look at free body diagram of m2, there is a downward pull m2g, then there is a tension in the upward direction. It is again equal to T because this is a continuous string and the pulley is a massless pulley. So for continuous string, the tension will be the same. Okay. Okay. Now if we look at the pulley itself, then there is one T that's in the downward direction. There is another T that is also in the downward direction, so 2T, and then there is another tension T1 or T dashed in the upward direction, so that will be T dashed. Okay, so this can be simplified as downward direction 2T and in the upward direction T dashed. Okay. So these are the free body diagram for each of these three. Okay. Alright. Now let's move on to Newton's first law of motion. So you must have studied the formal definition of the first law. A body continues to be in the state of rest or of uniform motion unless acted upon by an external force. Let's break that down. What this one says, if net force on a body, remember net force is a vector quantity, if net force on a body is 0, then the state of the body, state of motion, let's say, of the body remains unchanged. What does that mean? So if the body was at rest, it will continue to stay at rest. If the body was moving with uniform velocity, it will continue to move in uniform velocity. There will be no change. It's pretty simple actually. If net force on a body is 0 and force is mass times acceleration, you will learn that in the second law. So what that means, the net acceleration on the body is 0. So there is no external force acting on the body, so there is no net acceleration. So it will continue to be in a state of rest if it was in a state of rest before, or of uniform velocity if it was in a state of uniform velocity before. So this F net is equal to 0. This is also called equilibrium. Okay, what does that mean? That means if there are multiple forces, let's say F1, F2, F3 and such acting on the body, if the body is in a state of equilibrium, then F1 plus F2 plus F3, like that, all the vector sums will be 0. This is a good point. This is a good time if you want to quickly revise on our lecture on vector addition and subtraction. It will be helpful. What this also means is the net force in the x direction will be 0. The net force in the y direction will be 0, and net force in the z direction will be 0. Okay, now with this, let's solve some typical examples and you can see where we can apply Newton's first law of motion. Now let's solve some problems and demonstrate how we can utilize Newton's first law of motion. First problem, okay. So here's a string, there is a 2 kg mass hanging from the string, and there is another mass 5 kg hanging from the string. Question is, find the tension in both these springs. Okay, assume G to be 10 meter per second square. Okay, very good. So let's draw the free body diagram for this mass. Okay, first let's draw the free body diagram for this mass. So first is, there is, let's say m2g, the weight of the body, it is being pulled. So the force that is acting on the body is m2g. Okay, and then there is a tension T1 acting in the upward direction, right? T1. Okay, now let's look at this guy. The second mass, there is T1 acting on it downward. This tension is always acting away from the body, plus it is being pulled by gravity, so m1g. Okay, and then there is a tension T2 on the string, again acting away from the body. Okay, now since this is in equilibrium, the other thing is, in the question it will be mentioned that the system is in equilibrium. Okay, so since it is in equilibrium, T1 is equals to m2g. m2 is 5 and g is 10, so 50 newtons. Okay, and T2 will be equal to T1 plus m1g. T1 we already have 50, m1 is 2, and times 10 is 20, so this is 70 Newton. Okay, that's problem number 1. Let's take another problem. There is a mass, let's say 5 kg. It is held by a string here, and then it is held by a string here. Okay, and then again the system is in equilibrium. Okay, so there will be a tension T1 acting on the body in this direction, away from the body, and there will be a tension T2 in this direction, away from the body. Let's say it's also given that this angle is 37 degree. Okay, now let's draw the free body diagram for this mass. So what are the forces that are acting on this mass? There is a gravity acting, mg. There is a tension acting in this direction, T1, and then there is a tension acting in this direction, T2, where this angle is 37 degrees. Okay, now since this is in equilibrium, we can say the component of T2 in this direction is what? T2 cos 37 degree is equals to mg, right? Net force in the y direction is 0. Net force in the x direction is also 0. So T2 sine 37 degree is equal to T1. Okay. Now sine 37 is very simple. If we draw a right angle triangle, if this is 37, this is 3, this is 5, and this is 4. Okay. Alright. So we can say then 1 and 2. So we can say T2, so 1, T2 cos 37 will be 4 by 5, equals mg 5 times 10, or T2 is equals to 25 times 10 by 4. Newton. Okay, and from 2 we can say that T1 equals T2 sine 37, so T2 is 62.5 and sine 37 is 3 by 5. Okay. Okay. Let's say take the next example. Let's say there is an inclined wedge. Okay. This angle is theta. There is a mass m. Okay. And it is held by a string here. And again the system is in equilibrium. Okay. See, we are able to apply the Newton's first law of motion because we are saying the system is in equilibrium, which means all the forces acting on the mass m cancel out. The net force is 0. That's what we are doing here. Okay. So it's very important that system is in equilibrium, that is satisfied to be able to apply Newton's first law of motion. Okay. Now let's draw the free body diagram for this mass m. Okay. Now obviously there is a gravitational pull that is acting on it. Okay. Then there is a normal force that this wedge is exerting on the mass. Okay. And the third is, so there is a gravitational pull, there is a normal force here, and the third is this tension in the string. The tension in the string is this side. Okay, and the tension is always away from the body. Okay, now if this angle is theta, this angle is also theta. Okay, this angle is 90 minus theta. Okay, so if we have to apply the laws of equilibrium here, which means all the forces cancel each other out, let's do a component. Now we can assume the x-axis and y-axis in any direction. Let's say this is the x-axis and this is the y-axis, right? These are perpendicular. So basically along the edge of this wedge it's x-axis, and perpendicular to this edge of this wedge it's y-axis. So what is component of mg in the y direction? It is mg sine 90 minus theta. Okay, so what are we trying to do? We are trying to find the component of mg in this direction and the component of mg in this direction. So this one is mg sine 90 minus theta, which is what? Which is mg cos theta. Alright, and in this direction it's mg cos 90 minus theta, which is mg sine theta. Okay, so we don't really need to always do this calculation. You can memorize that the component of mg in the normal direction, in the perpendicular direction to the edge, is mg cos theta if this angle is theta, and the one along the edge of this wedge is mg sine theta. So because the system is in equilibrium, n must be equal to mg cos theta, and T, the tension in this string, must be equal to mg sine theta. Okay, you can remember this one. Okay, let's do another example. Let's say we have a wedge theta. We have a massless pulley here. There is a mass m1, and then there is another mass which is hanging here, m2. Okay, system is in equilibrium. What we need to find out is what is theta, what is the normal reaction on m1, and what is the tension in the string. Okay, so if we draw the free body diagram of m1, so we know this side will be m1 g sine theta, this direction it will be m1 g cos theta. We have a normal reaction that is working on it, n, and then there is a tension away from the string is T. Okay, if we draw the free body diagram of m2, m2 in the downward direction force is m2g. Since this is a massless string and a massless pulley, the tension will be the same, so T. Okay, so the equations would be T equals m2g, so we can find out T. Now T equals m1g sine theta, so sine theta n is m1g cos theta. We already know theta, so we can find cos theta, so we can find the normal reaction. Okay, the last example we'll go over today is when we have a block over a block. Okay, let's say we have a surface, we have a mass m, and there is another small mass m on top of this. Okay, the question is find normal reaction between the two bodies and normal reaction between the surface and mass m. Just make sure you apply all the principles that you've learned so far. Let's do the free body diagram of small mass m. So gravity is pulling it, mg. There is a normal reaction that this mass m is giving on the small mass m. So let's say that's n, or let's say n1. Okay. Are there any other forces that are acting? I don't think so. Now, this is for mass m. Now let's look at mass capital M. Now gravity is pulling it in the downward direction, mg. Okay. This surface gives a normal reaction N2 on the mass, but then something else also happens. So if you look at this surface, this mass is pulled mg, and what happens is the big M, it has a reaction on the small m, n1. Now because this gives us normal reaction n1 on m also gives a normal reaction n1 on big M. Okay, so another force that is acting on this is n1 in the downward direction. Okay, many students make the mistake, they say that mg is acting on m. This is incorrect. It's actually n1 that is acting on big M. This is the correct answer. Yes, it turns out that n1 equals mg, but the interpretation is not that the force small mg acts on big M. It is n1 which is the opposite reaction, because m has a normal reaction and small m n1, m has a equal and opposite reaction n1 on big M. Okay, so just make sure of that. Now the rest of the thing should be simple, because it is an equilibrium, n1 equals mg, and in this case n2 equals mg plus n1. Okay, so these are some simple examples that we went over. So we learned net force acting on a body if it is equals to 0, then the body continues to be in a state of rest or of uniform motion, number 1. We learnt about the normal reaction force, we learnt about the tension force, we also learnt about the gravitational pull. Remaining types of forces we will learn subsequently. We will end the lesson here for today, and we will see you in the next lessons.